So we will start. Madam, we can start.
Yes. A warm welcome and fine good morning to one and all gathered here. It's a true pleasure for me to welcome you all to the DGL Distinguished Guest Lecture on Fourier Transform by Professor Vittal Rao, a former professor of mathematics, Indian Institute of Science, Bengaluru. So exactly 1 month back, we have a lecture on, CNC lecture by our chief guest, Professor Vittal Rao sir, took us to 18th century and virtually presented the life of the famous mathematician and physicist Joseph Fourier, and also explained the cause for Fourier series. In continuation with that, today we are having DGL.
Good morning.
And we are going to, Sir is going to discuss about Fourier transform, which is a mathematical technique that transform a function of time to a function of frequency. So not taking much of your time, I just transferred the talk to Professor Vittal Rao, sir. Please, sir.
Yeah, can I start?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So good morning to all of you. Thank you very much for this opportunity to talk to you about Fourier transforms. As Mahalakshmi said, this is a continuation in a sense of the previous talk on Fourier series and life of Fourier. This is not to be interpreted as a course on Fourier transform by any stretch of imagination. At best, you can think of this as some outline for a course, possible course on Fourier transformations. At the end of the lecture, some of you may feel that certain aspects of Fourier transforms, which are very close to your hearts, were not discussed at all. But considering the limit of the time that I have, I, as the speaker, have taken the privilege of choosing some of the topics which are closer to my heart. And so with this, I have taken a blanket refuge for all my omissions and commissions. So let me begin my talk. Next slide, please. Okay, it'll be a brief historical remarks. Yes, next. Yeah, the original idea of integral transforms came from Leonhard Euler. He introduced the integral transforms in the context of second order differential equations. The main idea was you start with a function f and transform it to another function, which I always denote in this talk, denote the transform by a capital F. And since the transformation involved integration, he called it integral transforms. And then you want to go back from the transform version to the original version. So he wanted to have an inverse transform. The idea he had in mind was, if you have a differential equation in F, you transform it, you get a new equation in the transform variable F. Supposedly and hopefully the transform that you introduced is good enough that the transformed version of the equation can be solved and you get the transformed version of the function, and then finally hope you to invert and get the solution F. This is the general idea of applying integral transforms to differential equations, which Leonhard Euler, he was the first to introduce this idea way back in the beginning of the 18th century. Next slide, please. Then it essentially, the idea of Fourier, when he started his thesis or memoir on heat conduction equation, he introduced the idea of Fourier integral, which is essentially the limiting version of the Fourier coefficient idea and the Fourier series idea. In the Fourier series, we had a sum. Now you let the period go to infinity, and then he gets the sum becoming an integral, and the corresponding coefficients become integral formulae. And he showed that the function can be expressed in this format. This is the original version of Fourier. Fourier never used the word integral transform or Fourier transform. Yes, next slide, please. Now again, in the sine and cosine, if you use the exponential for sine and cosine and substitute sine and cosine in the exponential form, he eventually will get fx equal to this format, which is our familiar Fourier inversion formula, and the capital F is this, which is our very familiar Fourier transform formula. Now, when Fourier did all these things, it was very ad hoc and very heuristic and non-rigorous. That's why he got criticized very heavily by the committee that examined his memoir. The reason is obvious because at the time Fourier did his work, the theory of integration, definite integrals, was not at all developed. It came after Riemann, after Fourier, when Riemann developed the Fourier integration, definite integrals, and subsequently a formal theory of integration was developed, measure and integration was developed by Lebesgue in the beginning of the 20th century. It is only after that things started getting very formalized and proper mathematical treatments were given to these ideas. And in 1910, Plancherel defined what is known as, worked on what is known as the Fourier transform of finite energy signals, or L2 or functions. I'll come to that a little later. And of course, he came to that in the context of getting an isometry on the space of L2R. Not really as an integral transform with the idea that Euler had. Okay. And subsequently, the modern treatments were given by Paley and Wiener somewhere in the 1930s. Next slide, please. As far as Fourier transforms are concerned, reasonably good theory after Plancherel was available for L1 functions and L2 functions, that is integrable functions and square integrable functions. But for other types of functions like P integrable functions, things were very, very difficult, and things had to wait till the distribution theory was developed. The distribution theory was developed first by Sobolev in 1936 and was consolidated by Laurent Schwartz, the French mathematician, in 1940. Then the idea of distribution of the Fourier transform of distributions came in. So the idea of a function had to be interpreted in a more general sense, and then the idea of Fourier transform for this more general version of functions had to be brought in. So this brought in the theory of Fourier transform for distributions, and hence we could find the Fourier transform of LP spaces because we could identify them with some distributions, and then through the distributions we could find the Fourier transforms. Essentially, there was a connection between the Fourier transform of an LP function with the LQ function. Okay, so it is a very loose statement. This has to be properly stated when you do a formal course on these things. And subsequently, we had the Fourier transforms in the n dimensions also, essentially the same idea, and which helped us to get into the modern theories of partial differential equations. And subsequently, these differential operators were generalized to the notion of pseudo-differential operators using the idea of Fourier transforms in the 1960s. The work was very nicely developed by mathematicians like Louis Nirenberg, who got the Abel Prize in 2015 and who just passed away recently on January 26th of this year at the age of 95. And there were others like Boccobza and Unterberger and so on. They developed in the 1960s onwards the theory of pseudo-differential operators, giving us a more general version of the idea of distribution, differential operators. I will briefly mention about these things a little later. Yes, please. Next slide. Plancherel was the first to use the term Fourier transform in 1915. Until then, nobody had used the word Fourier transform. It was Plancherel first. Then Tishmars, the British mathematician, used the terminology Fourier transforms in the 1920s. There was essentially after Fourier wrote his memoir, the book, a treatise was written by Xavier Schlomilch in 1848. This was a very comprehensive treatment of Fourier integral. Still, the word Fourier transform was not used. And it was very influential, for almost 80 years, right up to the first quarter of the 20th century. This book had the influence. Everybody used this treatment. Even the famous book of Karsla and Jaeger, which was written in 1906, follows closely the treatment of Schlomilch. In the third decade of the 20th century, Fourier transform became not only an important topic of research in mathematics, also in very many applications. There are 4 important books that were written in the 1930s in Fourier transform with all the modern versions: Bochner, Wiener, Paley-Wiener, and Tishmars. For those of you who are interested in the history of the Fourier transform, there is a nice article which I refer to in IEEE. And at the end of that article, there are several references to articles by M.A.B. Deakin, who deals with the history in an extensive manner. This is a very nice reference. It is easily downloadable, the IEEE paper. But the Deakin's paper, you got to do a bit of hunting to get them. Okay. So those interested may refer to this IEEE article and the Deakin for a comprehensive history of Fourier transform. Yes, next slide, please. Now, the Fourier's viewpoint was slightly different from Euler in the sense that Euler used it for differential equation. Yes, Fourier also used it for differential equation, but the way he looked at it is, I would interpret it as follows. It is in the modern language, we can call it as analysis and synthesis of functions. You are given a function f of t, you analyze that function to get some representative data about that function. Okay, for example, in the case of periodic functions, the Fourier coefficients are the representative data of the function. In the case of aperiodic functions, the Fourier transform is the representative data. In the case of discrete Fourier transform, it is a discrete periodic functions that for which we use the discrete Fourier transform. Now, once we have the data, we analyze the data. From that information, we synthesize back the function, that is reconstruct the function. The reconstruction process is the Fourier series. Knowing the Fourier coefficients, we construct the function back through the Fourier series. In the case of a periodic function, knowing the Fourier transform, you use the inverse Fourier transform to construct the function back. And in the case of discrete periodic functions, we use the discrete inverse Fourier transform to construct the original function. So you use this idea of analyze and synthesize. You extract some information about that function, which is essentially contains all the information about the function, and analyze that essence and then reconstruct the original function by an inverse process. Yes, next slide, please. In fact, this idea of analysis and synthesis is essential, is a very important aspect of all signal processing or anything, any such function processing these days. Okay, next slide, please. Yeah, in Fourier's point of view, analysis means you have to extract certain representative data. Yes, next slide, please. How do we do that? As I explained, if you have a periodic function, you extend the get the Fourier coefficient as the representative data. If you have an aperiodic function, you get the Fourier transform as your representative data. If you now look at the Fourier series, the Fourier coefficients At the time, Fourier was highly criticized because of the fact he did not explain for what functions this integral is defined, how is it defined, and so on and so forth. But subsequently, now we know this integral is well defined when the function is integrable, absolutely integrable. And not only that, these representative data called the Fourier coefficients are well behaved in the sense they belong to C not Z. C stands for convergent, 0 stands for convergent to 0, Z stands for they are defined for integer values. So Fn is a convergent sequence converging to 0, that is the Fourier coefficients converge to 0 and then goes to plus or minus infinity. The faster they go to 0, the better the reconstruction will be. And that's all the major theorems about convergence and the rates of convergence of Fourier series that was in classical analysis. In the case of Fourier transform, the representative for aperiodic functions, the representative data is the Fourier transform. Just as in the case of Fourier series, this is also well defined when the function is absolutely summable. In the case of Fourier series, it was convergent to 0. In the case of Fourier transform, the function is now a function defined on a continuum. Omega varies over minus infinity to infinity, unlike the Fourier coefficient case where n varied only over the integers. Here again, it converges to 0 when the argument goes to infinity. So both are well behaved at infinity, and the faster, the better behaved, that is the faster they go to 0, better will be our synthesizing process. Next slide, please. So now we have Fourier's coefficients and Fourier transforms are the analysis part. The synthesis part, that is knowing this, how do you construct the function? Next slide, please. So in the Fourier series case, once we know the Fourier coefficients, these Fn's, we construct the function by means of the Fourier series, and there'll be convergence questions. Again, this was raised to Fourier. We was not able to answer properly. Then it came to Dirichlet, and Dirichlet gave the right conditions and said that if these conditions are satisfied, this series will converge to the average of the right and the left limits. And since at the point where function is continuous, right and left limits are same, it will converge to the function. So for when the function satisfies Dirichlet condition, absolutely no problem about convergence. And same situation even in the Fourier transform case. This is the representative data is the Fourier transform, and this is the reconstruction process, the Fourier inverse transform. Convergence, again, Dirichlet conditions, same type of convergence. Then, in the case of a periodic function, if a function is P integrable, that the pth power is integrable, it is also L1, and therefore already we know that for L1 everything is nice. So if everything is nice for L1, then everything is nice for LP. But we don't have that luxury when we come to Fourier transform, because our interval of integration is the whole line. It's an unbounded interval. Problems start. In the case of Fourier series, the interval was only a finite bounded interval. In the case of now Fourier transform, our interval is R. The domain of definition of the functions is R. It's an unbounded interval. So we don't have the luxury that P integral implies one integral. And therefore, right from knowing the Fourier transform of F in L1, we cannot talk about Fourier transforms of functions in LP. This is a very serious problem in Fourier transform, which takes quite a lot of hard work to get settled. Yes, next, please. Now, let me first, I said P not equal to 1. So let's take the special case P equal to 2. This is always a nice case because it gives you the Hilbert space structure. So if you have a function, which is, this is what engineers know as finite energy signals. If you have a finite energy signal, periodic, this should be 0 to pi. I mean, this R is wrong because I'm in the Fourier series case, it should be 0 to pi. The Fourier coefficients are well defined, and the Fourier series converges in the root mean square sense. And about 50 years back, Carlson showed the series also converges almost surely. That is, almost everywhere it converges. But whereas in the Fourier transform case, the function being in L2R does not allow us to conclude that the function is in L1R. Therefore, we cannot jump to the conclusion that the Fourier transform is defined. So Plancherel had to do a hard work and eventually show that the Fourier transform is defined only in the sense what is known as limit in the mean. L dot I dot M means limit in the mean. That means you take this finite interval minus n to n and look at the integral only in that finite interval part, you get a function which depends on omega and n. So I call it fn omega. So I get a sequence of functions. Now this sequence of functions, because now we have finite interval, is well defined, and this converges in RMS sense to some function, and that limit function is called the Plancherel transform or the Fourier Plancherel transform. So you have to do a sort of approximation process in order to get the idea of the Fourier transform of a finite energy signal. It's not easy. And similarly, for the inverse transform also, a similar limit in the mean process has to be done. Take the truncated integral and then look at the function defined by the truncated integral. That gives you a sequence of functions that will converge in RMS sense to the original function fx. So the Fourier transform of L2 functions is already a difficult process. And if somebody is interested in knowing all the details of this, it's a very nice idea, but I don't have the time to go through that. One can see Rudin's real and complex analysis book for this. Okay, next slide, please. But things get even more complicated when p not equal to 2. In the Fourier series case, again, everything is nice. And even in immediately after Carlson, Hunt even showed, I mentioned this in the last lecture, that the Fourier series converges almost everywhere. But in the case of Fourier transform, the p equal to 1 case was okay. P equal to 2 case was handled by Plancherel. But the p not equal to 2 case is even more difficult, and it leads to the realm of Schwartz spaces and tempered distributions. And I don't think I'll have the time to discuss this. So this is the modern versions of Fourier transforms. You have to get into distribution theory. Yes, next slide, please. Now I'll skip this. Everybody knows discrete Fourier transform. In this case, the transform function, original function, both are vectors, finite component vectors, and the transformation is done through the so-called DFT matrix, and it involves the nth root of the identity matrix. And so it's basically in the realm of linear algebra because it's just matrix multiplication. The interesting thing is matrix is so nice, its inverse can be written by inspection. Okay, that's a very nice this thing, except for a factor, it's a unitary matrix, and therefore the inverse can be immediately written down. Yes, next slide, please. Okay, of course, we all use all kinds of properties of Fourier transforms in our work, whether we are doing differential equation, signal processing, or whatever, PD or ODE or whatever it is. But we must remember that already the definition itself has so much difficulty. Even the inverse for L2 function, there is a lot of difficulty. For LP function, there is a lot of difficulty. But therefore, what the standard properties state should be properly interpreted, and for each kind of function, the interpretation must be properly given, should not be taken very lightly. Yes, I'll just go through some of the standard properties which we use. Okay, yes. Okay, first thing I mentioned was the fact that the Riemann-Lebesgue lemma, that is, at infinity, the Fourier coefficient and the Fourier transform behave well. They converge to 0. And then this idea of translation and multiplication by exponential, these are dual properties. Translation on one side boils down to multiplication by exponential, and the translation on this side boils down to multiplication of the exponential on this side. And similarly, time reversal boils down to omega reversal. and reverse one. And this the property is what is used by differential equations people. If you have the kth derivative of a function, then the Fourier transform simply gets multiplied by I omega to the power of k. And similarly, derivative on the Fourier transform side transform to multiplication on the time side. The time and frequency is an engineer's terminology. For mathematician, both are real variables. That's all. T and omega are both are real variables. Therefore, f of t and f of omega are both functions of a real variable. Okay. Now, it is this property that converts a differential equation into an algebraic equation. The differential equation for f, little f, will be converted to an algebraic equation of capital F. Calculus is converted to algebra. And this is what the original idea of Euler was, to have a transform which converts the equation to, in the transformed version, to a nicer one. People were more familiar handling algebraic equation, so they considered that is better. So solve the algebraic equation and try to get the capital F, and from the capital F, recover your original function. Yes, next slide, please. Back. Yes, this one. This is another nice property. This is all due to Plancherel, that the dot products are nicely preserved. See, this factor, this 2 pi is a headache factor in Fourier transform. Different people put the pi in different places. Depending on that, this formula will be slightly different. This is what I call it as standard, but there is nothing standard in this. Okay, so the dot product on the time side is essentially dot product on the frequency side. And similarly, the Parseval's formula, this is what Plancherel was looking for. That is isometry. The lengths are preserved. So that's why you put the root 2 pi in a different place. Then if the length on the t side will be the same as the length on the omega side, or the norm on the time side will be the norm on the frequency side. So this is a very important property that he was looking for, Plancherel was looking for from the point of isometry. And this Plancherel formula and the Parseval formula show that the Fourier transform can be properly defined on finite energy signals such that it becomes an isometry. Okay. And of course, the property of the convolution converts it into an algebra. Okay. Convolution on one side becomes simply multiplication on the other side. And this helps us again to clean up certain frequencies in the signal by convoluting with the right type of signal or right type of filter or whatever you want to call it. Okay, next slide, please. Next slide. Okay, I will just take two properties of Fourier transform. We can slightly modify this and convert it to the Fourier series also, but we'll not worry about it. The first one is the scaling. What happens when you scale the function on one side? Instead of t, I have at. Then what? There is a scaling on the reverse side in the transform side. I had at here, I have omega by a. Here a was in the numerator, here a in the denominator. Of course, there is another factor, modulating factor here. So scaling, this is important when you study later the structure of wavelets and wavelet transforms, etc. And then the next is a very important property again in Fourier transform. Suppose I take the Fourier transform of f. As I said, for me, omega is again a real variable. So I'll write the Fourier transform as also as a function of t, where t is the real variable. Instead of omega, I'll write t. So again, I have a function defined for real variables. I can take the Fourier transform of this Fourier transform, which is this, and now you compare it with the inversion formula, that is nothing but 2 pi f minus omega. So the important conclusion is the Fourier transform of the Fourier transform is 2 pi times the original function with minus sign attached to it. Therefore, if you do it again, Fourier transform of the Fourier transform of the Fourier transform of the Fourier transform 4 times, you will come back to the original function with a 4 pi squared factor. And that tells you a lot about the eigenvalues and the eigenvectors of the Fourier transform operator. And the last one is a very important property in the idea of when you go to distributions and the idea of distributions, it tells you how to define Fourier transforms, is that if you take a function and its Fourier, another function, Fourier transform, mixing a function and a Fourier transform. You take a function and the Fourier transform of another function, the integral we can interchange. You put the Fourier transform on the other function and take the original function. So f times the Fourier transform of g integral will be equal to g times the Fourier transform of f integral. So the Fourier transform can be switched between the two functions in an integral. This is a very important property which suggests the definition of Fourier transform in the realm of distributions. Yes, next slide, please. Now, one of the reasons why this Fourier transform became so successful in applications was its sweeping general application to what are known as linear continuous systems, time invariant system. First of all, what is a linear system? Suppose you have a periodic function and you input it, you get an output which is a periodic function. And then we say it is linear if superpositions are preserved. Okay, if you put a superposition of functions, the output is the superposition of the individual outputs. And this is an important property, continuity, which normally people don't mention, but without this you can't proceed. Okay, so whenever you have a sequence of functions which converge here, the corresponding outputs will also converge. Then we say the system is continuous. That is, infinite superpositions are preserved. In mathematical language, this simply means that this is a continuous linear operator on the space of L2, 0 to pi. That is the standard terminology which a mathematician will use. It's the L2, 0, any continuous linear operator on L2, 0 to pi is a linear system. Next slide, please. Another important operator that is the translation operator, time shift. If you have a function f, you put it through this translation, then you get the time gets shifted to t. The output is where the time gets shifted to t minus tau. Yes, next slide, please. So what we are interested in is where we combine both. So suppose I have a function f, then I put it through the system, I get an output, then I translate, I get something. On the other hand, I do the reverse. First I translate, I get this, then I put it through the system, I'll get the same result. Okay, such a system is called a linear time invariant system. That is, in the mathematical language, the shift operator and the system operator commute. Whether you apply the linear system operator first and the shift operator later, or the shift operator first and the system operator later, the result is going to be the same. So the shift and the system commute, then it is called a linear time invariant system. Yeah, next please, next slide please. The important thing is that such systems can be analyzed by means of what is known as the impulse response function. Here again, it's a little bit loose what I'm saying, because one has to remember that this delta has to be interpreted in the language of distributions if you want to do it mathematically. But anyway, if I put the delta as an impulse to the system, some output comes. We call it ht, and that is called the impulse response function. Now, if you put a shifted delta, shifted impulse, then we know that because it's LTI system, the shift goes to shift. Okay. So the delta t minus tau will get an output ht minus tau, and delta t will get an output ht. Yes, next slide, please. So now let's look at this for a general function. If I have a function f, if I put it in the system, I'll get an output f. But this function can be expressed in terms of the delta function as the integral with respect to the delta minus s. Now, if I put through the system, this does not depend on t. The only dependent is on this. This is the shifted one. Shift and system is the same as system and shift. So I get this integral. So these two are equal. So the output can be written as this. So therefore, the system operator is essentially a finite convolution integral operator. So there is a whole lot of theory about finite convolution integral operators. So the system operator for linear time invariant systems can be completely captured by this kernel ht minus s, which, or in other words, ht convolution with ht of f, where ht is the impulse response function. So it is the impulse response function that captures the entire action of the system, linear time invariant system. Yes, next slide, please. Now, the important thing is once you have such an operator, a mathematician always looks for the eigenvalues and the eigenvectors of the operator. So if I want an eigenvalue and eigenvector, SF must be equal to lambda f, but SF is written in the term of this integral. Just now we saw system response must be equal to lambda f. Now we apply the convolution theorem. This becomes the product in the transform side, and this becomes the lambda fn. So combine the terms, you can write it in this form. We want an eigenvector and eigenvalue. So since eigenvector cannot be totally zero function, this fn cannot be zero for all n. So for at least one n, fn should be not zero. In that case, this term must be zero. So lambda must be equal to hn. So every one of these hn values becomes an eigenvalue. So the eigenvalues are all hn. Every Fourier coefficient of the impulse response function becomes an eigenvalue, and the corresponding eigenfunction is the exponential function. See, notice that the eigenfunction does not involve anything about the system. It is a standard function 1 by t to 2 pi e to the int. It has nothing to do with any information about the system. So the eigenfunctions are the same for all LTI system. That's the beauty. And therefore, eigenfunction expansion means expansion in terms of these exponentials, which is exactly Fourier series. Therefore, Fourier series becomes an important ingredient to study LTI systems, because that gives you the eigenfunction expansion of for outputs in the system. So it is eigenvalues that differ for different systems, because eigenvalues are given by the impulse response. The impulse response will be different for different systems. Therefore, it is the eigenvalue that is different, but the eigenfunctions are all the same for all LTI systems. No matter what LTI system you take, the eigenfunctions will be the same. The corresponding eigenvalues will be different. And as I said, the Fourier thing is just the in terms of the expansion. Yes, next slide, please. I can go through this fast. This is the same thing in the case of aperiodic function. Next slide, please. Again, we have the system and the impulse response and the shifted response. Yes, next slide, please. And again, we have that the function goes to this, the impulse response goes to this, and therefore the system operator is a convolution operator. Now it should be minus infinity to infinity, because now I am in the general case. Okay, keep going. Next. Then again, in the eigenvalues, eigenfunction case, in the case of aperiodic functions, we had hn, fn in the case of periodic case. Now we have h omega, f omega, f omega, and therefore we get this equation. Previously, all hn were eigenvalues. Now all h omega are eigenvalues. That's where the Fourier transform plays an important role. The eigenvalues of an LTI system with aperiodic inputs are all exactly the values of the Fourier transform of the impulse response function. And the corresponding eigenfunctions, again, they are the same for all LTI systems. They are 1 by 2 pi e to the I omega t. So eigenfunctions are same. It is the Fourier transform, inverse Fourier transform is just the eigenfunction expansion. But one thing you must note is that in the case of periodic functions, we got the eigenfunctions e to the int. In place of omega, I had n. So e to the int was also a periodic function. Whereas suppose now we consider the LTI system with finite energy signals, then this eigenfunction e to the I omega t is not finite energy over minus infinity infinity. Because if you integrate the modulus squared over minus infinity to infinity, you get infinity. So we get into a very strange situation. The eigenfunctions are no longer in the same space, L2. It has to be interpreted in a very careful manner. And that's where either you get into the notion of singular eigenfunctions or the idea of distribution. So these things have mathematically have to be handled with care. Okay, right. Okay, next slide, please. The next idea where Fourier transform plays an important role in application is interpolation. Let me go through this. Suppose I have a 2 pi periodic function for which the Fourier coefficients are all 0 beyond a certain stage. So beyond a certain stage, all the Fourier coefficients are 0. So if I write the Fourier series for the function, so all those terms beyond a certain stage will be 0. So I will only get k equal to minus n to n. Now I will write this I'll write e to the IKT as z to the power of k, where z is e to the power of it. Now there is the lowest term is z to the power of minus n. Pull it out, then all will be positive powers. You will get a polynomial of z with order 2n. So the Fourier series simply represents the function f as a polynomial in the variable z, where z is e to the power of it. This polynomial is degree 2n. And the important thing to observe is if I want to recover my function f, I know this because z is e to the power of it. The only thing I should know is p to the power of pz. So in order to recover the function, I must recover pz. But pz is a polynomial of degree n. So next slide, please. So the polynomial of degree n can be recovered by 2n plus 1 data. A polynomial degree 2n has 2n plus 1 constants. So we have to determine these 2n plus 1 constants. So we must know 2n plus 1 pieces of data. And that is the value of the function at 2n plus 1 points. The question is how cleverly you choose these 2n plus 1 points. And Dirichlet showed for these periodic functions, the clever way is to choose these 2n points, k equal to minus n to n, this point. That is, you choose between minus pi and pi, put a point at 0, and between 0 and pi, choose n points equally spaced. Between minus pi and 0, choose n points equally spaced. And this d and t is called the Dirichlet kernel, which plays an important role in the analysis of convergence of Fourier series. That is how Dirichlet came to those Dirichlet conditions for the convergence of Fourier series. You can look at this as a very peculiar type of convolution. It's a convolution in which the function dn is defined for a variable which is continuum in an interval with a function f which is defined on a finite set of points. Okay, so this is a very peculiar convolution between a continuum defined function and a function which is defined on a discrete set. But note that essentially this is like in the form of a convolution, and also in terms of the values of the function at 2n plus 1 point. So once you know the value of the function at 2n plus 1 points, for such functions, we can recover the function by means of this Dirichlet interpolation formula. So I'm not writing the Lagrange interpolation, I'm not writing the Newton interpolation, but Dirichlet said for periodic functions, this is the right interpolation. By sampling the function at these 2n plus 1 points, we can recover the function f of t. Yes. The continuous analog was this, the famous sampling theorem of Shannon-Nyquist. In the case of aperiodic, we said the Fourier coefficients are 0 beyond a certain stage. Now we say the Fourier transform is 0 beyond a certain stage. They are called band-limited signals, and they can be expressed. Here again, you can see a kind of convolution, a t minus n, fn, a discrete and a continuum. There we had the Dirichlet kernel. In place of the Dirichlet kernel, we have this cardinal sign. This is called the cardinal sign function or the sinc function. So the interpolation formula was there long before Shannon and Nyquist. It was done by, I think it was probably an exercise in a book by Haar in interpolation. And So it had to be interpreted carefully and brought to this level eventually as a sampling theorem for signals. Yes, next, please. Now, again, we looked at Fourier transforms from different points of view. We looked at LTI systems. We looked at sampling and interpolation. Now I'm looking at it very, very clearly from the point of view of basis. Yes. Yes, next slide, please. So one of the important problem is how nicely we can express a given function in terms of simple functions. Of course, it doesn't means what do you mean by nicely represent and what do you mean by simple functions? Yes, next slide, please. So first thing that came after calculus was Maclaurin. He said the function can be expressed in powers of x. If the function is very smooth, up to n degrees of derivatives available, you can have the nth order approximation. If you have more derivatives, more smoothness, we have an infinite series approximation. Yes. Next slide, please. Taylor said you can expand it in terms of not necessarily in the neighborhood of 0, you can expand it in the neighborhood of a. Depending on the number of derivatives and the smoothness, you can get better and better approximation. Yes, next slide, please. Now, in this Taylor and Maclaurin, the representation involved derivatives. Derivatives are calculated by taking limit h tending to 0 in that neighborhood. So therefore, only the values of f in the neighborhood of the function are used, and hence these are all useful only for local analysis. They don't worry about what happens far away from that point. Secondly, these are not derivatives are always difficult to compute. So you must remember that Taylor and Maclaurin are good for local analysis and not very good from the point of view of computations. In Maclaurin approximation, essentially what we are doing is we are expanding it in terms of powers of x. So that is what is we are using it as a basis. The powers of x functions, these are used as basis functions. Next slide, please. Now, I said that these are used only locally. Therefore, to avoid this problem, we take these functions x to the power of n, we orthonormalize them over inner product space. Yes, next slide, please. We get an orthonormal polynomials. And by doing over different intervals and different weight functions, we get different spaces. And the expansion will be always of this form, an, phi, n, nx, where an is the dot product with the orthonormal function. Wx is just the weight function. The weight function is introduced because if the interval is infinite, x to the power of n will not have finite interval. So in order to bring it down, we'll have to put some exponential type decay at infinity in the weight function in order to make x to the n integrable. Okay, next please. Instead of polynomials, we can take any orthonormal basis and we can expand a function in L2 in terms of the orthonormal basis. The coefficients will be given in this again as the dot product of the function with the orthonormal basis vector. Yes, next slide, please. What we are doing in Fourier series is simply doing orthonormal expansion. The function that are chosen are the orthonormal basis that is chosen is this Fourier basis 1 over root 2 pi e to the inx, where n varies from minus infinity to infinity. So Fourier series is only just a special case of the general orthonormal ideas. Okay. Now you see the coefficients are computed by using integral minus pi to pi fx. So we use the information about the function on the entire interval minus pi. Unlike Maclaurin or Taylor, which uses only local information. So Taylor and Maclaurin are good for local. Fourier or the Fourier transforms are better for a little bit global analysis of a function. Yes, next slide, please. Now I'm going to look at a very special orthonormal basis. I lost, okay. Take a function whose Fourier transform is this, which is 1 between minus pi and pi, 0 elsewhere. And you do the inverse Fourier transform, you get the function sine pi t by pi t. Now, the Fourier transform by shifting this function, you shift this function by n, pi t minus n divided by pi t minus n. Shifting boils down to multiplication by exponential. Now take two different n's. Look at the inner dot product here. The dot product in the t side can be converted to dot product in the omega side, where it's easy to calculate, which is 1 if m equal to n, 0 if m is not equal to n. Therefore, this sequence of functions is orthonormal. This sequence of functions ft minus n will give you an orthonormal sequence. Next slide, please. So what the sampling theorem says is essentially, if you have a band limited function, it can be expanded in terms of this orthonormal sequence. That's all that the sampling theorem says, that the sequence of functions we constructed above, they form an orthonormal set for the band limited functions, but there is a technical reasoning. Band limited functions are dense in L2R, so every L2R function can be expanded in terms of these functions. So essentially, therefore, what the sampling theorem says mathematically is that this sequence of functions, sinc pi t minus n, is an orthonormal basis for L2R. That is the essence of sampling theorem. Yes. Next, please. Look, I lost the screen. I lost the screen. Yeah. I'm losing the screen. Okay. So look at this basis. We have found all these functions are obtained from one function sine t by t by either scaling or shifting, either multiplication by pi and a shifting by n. So the entire basis is obtained from one single function phi t by dilation and translation. Haar had obtained a similar basis in way back in 1909, before all these came. Yes, next please. I'll quickly describe Haar's basis. Take a function which is 1 in 0 to half and 1 minus 1 and 0 to half. Then shrink it. Yeah, go to next slide, please. Next slide, please. Then you shrink it. Instead of 0 to 1, you take 0 to half and take half here. And then other part you take in the other half to 1. Yes. The next one, you further shrink it to quarter pieces. Yes. So you get a basis here. Next, please. Then you get a basis here. Next, please. Then you get the basis here. Then next, please. Then you get in the base here. So 4 pieces you got. Now you can get 8 pieces, 16 pieces by shrinking by diagonally dividing the intervals. And yes, please go on. Then you get a final basis for the interval. Please write 0 to 1. And you can make further translation beyond 1 and more extensions. You can get a whole basis for L2R. So Haar showed how to construct by starting from one function, which we had half between 0 and half, 1 between 0 and half, minus 1 between 0 and half. From that function, by dilating and shrinking, he could get all the, see here is a shifting and here is a dilation. This is only to normalize to length 1. So this is the dilation part, this is the shifting part. So by dilating shifting a single function psi, you could get hold of a whole basis for the entire space. Yes, next slide, please. The idea of that now we have one on the one side Haar basis, on the other side we had the Shannon type sinc basis. There are advantages and disadvantages. The sinc basis was smooth, the Haar function basis was discontinuous. But the sinc function lives for a long time. It is non-vanishing in the entire interval, whereas Haar basis lives only in a short interval. So there is an advantage of this. So each basis has an advantage and disadvantage. We want to catch hold of the advantages of both sides and construct bases like this. And that is what led to the modern versions of window transform, wavelet basis, and wavelet transforms, which are essentially modern versions of generalizations of Fourier transforms or Fourier analysis. Yes, next, please. The last topic I will discuss is very quickly differential operator. So if you have a differential operator, like the second order differential equation, you can take the Fourier transform then this is original Euler's idea. The equation now becomes this in the transformed version, which can be easily solved algebraically, then inverted to get the solution. This is what the original idea of Euler introducing integral transforms. Next, please. So similarly, the nth order differential operator will have a similar structure by transforming Fourier transform. Yeah, next slide, please. You can skip this and go to the next. And same structure will come partial differential operators, except in the case that partial differential operators, if there are n variables, the integrations will run over the n variables, so it will be integration over Rn. Now notice that this Pw is a polynomial in degree n. Yes, next slide, please. Now, what we have seen so far is differential equation with constant coefficients. We will now look at what happens with differential equations with variable coefficients. Suppose you take a function and differentiate it k times, its Fourier transform is this, because Fourier transform gets multiplied by I omega when you differentiate. So now to get this function, I have to invert the Fourier transform, so I get this interval. So d, the kth derivative can be written in this form. So if I multiply by a coefficient, which is a variable coefficient, that can be pushed inside the integral, because the integral is with respect to omega, it has nothing to do with x. Now you combine terms like this, we get an nth order differential operator, and now you get the summation can be pushed inside because of finite sum. You combine all these functions and call it as a phi of x omega. So the nth order differential operator can be written in this integral form. So what it says is an nth order differential operator is a combination of the Fourier transform and an integral transform. So any nth order differential operator can be thought of arising out of a Fourier transform and an integral transform. Any general, if you take any general phi of, in the case of PDEs, the phi xw has this structure, akx I omega k. Note that this x variable and y omega variable are separated here. So variables are separated here. But suppose you take a general phi x omega here, then we get the notion of a pseudo differential operator. Yeah, next slide, please. So this is the general form of a pseudo differential operator. Every differential operator with constant coefficients or variable coefficients can be written in this form, but there are operators of this form which are not necessarily differential operators, because this function can have a more general form. Okay. Yeah. Next slide, please. Now let's look at this. We have looked at Fourier transform from Fourier analysis from various point of view. One is in the idea of representing in terms of sinusoids. The other is in the idea of representing in terms of eigenfunction expansion, as we saw in LTIs. Or we can look at this as an orthonormal expansion. Or we can again look at it as eigenfunctions of specific LTI systems. Or we can look at it in the form of interpolation, sampling theorem, signal processing. Or we can look at it in the form of basis, special basis, and wavelets. Or we can look at it in the form of ODE, PDE, pseudo-differential operators, etc. Or, which I have not even touched, we can talk about it as Fourier analysis on abelian groups, and particularly Fourier analysis on finite abelian groups and algebraic coding, or general harmonic analysis. So there are many ways of looking at Fourier transform, and if you get involved in one of them, you get immersed in this. In fact, if you interact with many of these people, you will find anyone working in one of these areas with insists that is what Fourier transform is. If you talk to a fellow in harmonic analysis, he will say that is what really Fourier analysis is. If you talk to a fellow in signal processing, he will say that is what Fourier analysis is. Or LTI signals and systems fellow will say that is where really Fourier analysis is. And if you permit me, all this reminds me of a few lines from a Tamil version of the Ramayana, the Kamba Ramayana. Yes, next slide, please. I will just quote a poem in Kamba Ramayana. In this, what Kamba does is he explains the scene where Rama enters the city of Mithila, and all the young girls who heard so much about Rama rush to the street to have a glimpse of Rama. And those whose eyes fall on the shoulders of Rama, broad shoulders of Rama, can't take their eyes off the shoulders. They are stuck there. Similarly, those who see the lotus feet, their eyes get stuck there, and so on. So eventually, when they argue within themselves, each saying that that shoulder is the real Rama and the lotus feet is the real Rama. And I think it is the same fate with the Fourier transform also. Each fellow who works in one area thinks that is what Fourier analysis is. But then finally, what the poet says is there anyone at all who has seen the true form of Rama? So you really, if you want to see the true form of Fourier transform, you must transcend yourself out of all these prejudices and look at every aspect of Fourier transforms and Fourier analysis to see the glorious form, the beautiful Vishwarupa of Fourier analysis and Fourier transform. Next slide, please. Similar sentiment is expressed by a French novelist. The real voyage of discovery consists not in seeking new landscape, but in having new eyes. The same thing like what Kamba says, that different eyes saw different things, but you have to have the new eyes every time to see all the things. My destination is no longer a place, but new way of seeing. So you keep seeing the Fourier transform in many, many ways, then you start appreciating it better. Yes, next slide, please. Yeah, this is one of my favorite quotes. Maybe one or two, the audience, there Arulalan is there in the audience. He's also very fond of this quote. See, Fourier was criticized for being very heuristic, ad hoc, not rigorous, etc., etc. But at the same time, the idea was his, and therefore, even after all the developments, it is only called Fourier transform. Add Plancherel and say Fourier Plancherel transform. You may say Fourier transform on distribution, but the word Fourier transform cannot be removed. So Hermann Weyl says, the discoverer who first breaks through often does rough work, and yet to him belongs the highest honor. Only after the lock is broken, one can study at leisure and construct a key that opens it more smoothly. That's what Lebesgue, Plancherel, Paley, Wiener all did subsequently. From a purely logical point of view, there is no reason why the streamlined method should not be invented straight away. But in the face of a profound problem, man is seldom clever. So anyone doing research must keep this in mind. Our first work, our first proof of anything, our first algorithm will always be very patchy, very clumsy, etc. But once it gives the result, that's it, you got it. Then you can sit down, smoothen it out, write it better, make it simple, and so on and so forth. But the first proof, the first idea is always the really valuable one. Yes, next slide, please. And finally, I will quote Shakespeare's Hamlet. There are more things in heaven and earth, Horatio, there are dreamt in your philosophy. I will conclude by saying there are more things in Fourier series and Fourier trans, my friends, than were mentioned in this talk. So I apologize for all those things not mentioned and apologize for all those things which are mentioned so poorly. Thank you very much for your patient listening. Yes, I am done.
Thank you very much, sir. Sir?
Yeah. Jamadagiri sir, would like to say something?
About the talk or about...
Yeah.
See,
both.
talk, I won't say much because I was patching listening because as I told you, all Wednesdays, I'm occupied from 9:30 to 10:30. The only thing to say is my suggestion to communication engineers in the audience is just look at what Professor Vittal Rao said about Fourier and just reflect on their own particular applications that they have done in communication systems. The variety that they see and then the beauty that they see should, I think, become extremely interesting. In fact, modulation theory is something which is so much built on Fourier, that I think it would be instructive to do a little bit of contemplation on that. And as usual, Professor Vittal Rao has laid the whole infinite ground, bringing lots of people and lots of ideas into the fore. And I think it leaves hours of contemplation that we can do on this mathematics and idiot. Thank you very much, sir.
Thank you.
So there's one question by Professor P.C. Deshmukh.
Yes,
Could you
sir.
please comment on the difference between FFT and the
Yes.
chip jet transform? What are the additional features included in CZT?
Chip zeta transform.
Yeah.
Hello.
Yeah.
Hello.
Yes,
Yeah,
sir.
yeah.
Yes, sir. Yeah, you're audible.
Yeah, but I didn't hear you.
Oh,
Yeah,
okay.
there's a
There is a question saying that can you please comment on difference between FFT and the chirp Z transform?
To be honest, I have no idea.
Okay.
That's why in the beginning I apologize to many things that I will not say.
Actually, Professor Vittal Rao mentioned that we all see through the narrow tunnel of our own areas. That's what happens to communication engineers. For them, everything is simply a signal and then a bandwidth and then the side lobes and things like that, which all actually map to Fourier
So
transform.
if you tell me what is that chirp thing, then I will connect it mathematically and see. But I don't know the definition, the word chirp.
Professor Jagadish wants to make a comment.
Yeah, yes, sir.
Yes, sir. Please.
I think
Imtiaz, please make Professor Jagdish as the co-host. Or open his permit him to
unmute,
do audio.
sir. Yes, sir. He
Audio,
can.
audio.
Yes.
Yeah. Jagdish, audio, just unmute it.
Sir, thank you so much, sir. It was so nice hearing to you after several years. I heard, I sat through your class in IAC.
Oh my God.
All of us.
What is very interesting is this Kambaramayana connection was fantastic. I think that is what all of us seem to be doing in whether it is aerospace where we do signal analysis or it's really very nice. Thank you so much. I just enjoyed it. I have no question. I just wanted to say that.
Thank you.
So there's one question by Madam Nandini. Which of the Fourier components would be useful for discriminating features?
What?
Discriminating features. Which of the Fourier components will be useful for discriminating features?
See, if you are looking at periodic functions,
yeah.
Okay. Essentially, you have to have the Fourier series. So the Fourier series, if you look at it has Fn times e to the int.
Yeah.
Okay. The e to the int has the length 1, modulus is 1. So its contribution is, see, the whole contribution is from Fn. So therefore, we have to look at how big Fn is in absolute value. So that is why we wanted to see how slowly, how fast it goes to 0. The faster it goes to 0, the smaller the number of Fourier coefficients, that will be enough to assess the function. But if it goes to 0 very slowly, then you have to take a large number of coefficients to take care of information about the function. But if you are with the aperiodic function, in the case of Fourier transforms, that is why the window transforms have been introduced. The idea of the window transform is you can do any type of specific, if you want a very fine information, you can take very fine windows, those particular bases which are focused at that particular point. Or if you want a very coarse information, you can take those basis vectors which are spread out large. And that is where all this dilation and translation comes into the picture. So the windowed Fourier transforms are useful in doing very fine analysis or very coarse analysis. You can choose the right basis vectors from among the basis vectors, depending on whether you want fine analysis or coarse analysis. In the case of Fourier series, the whole business depends on how fast does Fn tends to 0. Okay, so in fact, there are a huge number of theorems about this behavior of Fourier coefficient going to 0. There are a large number of theorems known as Tauberian theorems, which tells you about this behavior. So one has to take all these things into account before deciding on which are the right ones we are going to take into account.
Thank you, sir. There's one more question by Professor Radha Gupta. As a mathematics faculty, how should we motivate a second-year engineering student about Fourier transform? What could be the best example that can be given to them so that they understand why the topic has been introduced?
Sir, I answered it through the
I saw
message.
that, sir. I saw that.
Yeah. Actually, there are so many examples in the YouTube. You could take some unusual examples, usual examples, and so on. Just search for that, because it is the job of engineers and physicists who actually give examples to actually show how useful Fourier analysis can be. So it can be, for instance, there are a lot of things on signal compression and on picture compression. So many different kind of examples which you can take from any of these things.
Yeah, I want you to tell about the CSE lecture next week.
Okay.
Yeah.
Oh, but there is one more question. Will Maclaurin or Taylor expansion along with Fourier analysis be helpful in providing better time frequency understanding? Yeah, probably. Yes.
Yeah, you see, the thing is, when you go to war, you take all the arms that you have with you, okay? You just don't take one bow or one gun or one plane with you. You take everything that you have with you to attack a problem. So you have Maclaurin series on one hand, you have Fourier series on another hand, Fourier transform, sampling on other hand, and maybe even other transforms if you have in your hand. So everything, whichever is the right one, use it and kill it. That's all. Yes. Our job is to solve a problem. See, the difference between a mathematician and engineer will be, a mathematician will worry about, once he takes the Fourier transform, all its property, what are all the conditions, blah, 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 etc. And for an engineer, and in a broad setup, for an engineer, I want to solve this problem. I don't care whether Fourier transform is applicable or whether it is Merlin transform that is applicable. But what is it that is applicable, I will use and solve the problem. So therefore, you don't say that I will take only Maclaurin series, I will take only Fourier transform with me. Take everything with me and see which one is applicable for the problem. The broad guideline is, if you want very local analysis, then use Maclaurin and Taylor or nicely windowed transforms. If you want a global analysis, use the general integral transform, Fourier transforms, and wavelet transforms. That is the broad guideline. Yeah.
Sir.
Okay. Sir, again, thank you very much.
Okay.
For your wonderful talk. It was a little bit of a continuation of what Fourier did earlier.
Yes.
You did a Fourier lecture, so it was a continuation. Actually, from Bytes, we have a series of lectures which are called CEC, the celebrities and celebrations. These lectures, as the name indicates, it is to celebrate the life of a celebrity and really look at what was the contribution by the celebrity and under what circumstances did this person do it, and then what are the implications and so on. Now here, the definition of a celebrity, as far as we are concerned, is somebody whose contributions made a major impact on this whole world, preferably in the all the domains. It can be in the domain of art, can be the domain of science, can be in the domain of philosophy, domain of everything. And he or she must have set a new trend, which for a long time gave a lot of material for people to think about, to contemplate, to understand, and to apply. Now, there cannot be a better example than Fourier that you just listened to. He started something in 1800s, early 1800s, almost the end of 1700s, and it has taken about 170 years of work on what he started to really come to what you can say the final things about what he did. So the impact of him, if not anything, just on the amount of work that was created and the number of people who work like McLaurin, Lebesgue and so many other people, Blachel and others. And so we are talking about celebrities of that caliber. They start something, a new way of thinking, and this thinking provides material for the next 100 years, if not more, for actually coming up with new ideas, new applications, new understanding, and a new direction in life. So we have picked out a few names whom we thought were very impactful. Uh, People are welcome to suggest other names, but we have selected a few lasting for the next 3 to 4 years already, and we want to celebrate one per month. And coming up next week, exactly 1 week from now, is again by Professor Vittal Rao. He's going to talk on Everest Galwa. That Galwa, he started the whole groups and field theory from his not a longish life that he had. And then it has taken almost 150 years to realize the importance of what he has done. And he has now penetrated all fields. See, Galwa's applications in physics, then in engineering, then in computers, and every kind of thing. So we are going to hear about what did Galwa do, what is the importance of his thinking, and most importantly, how his thinking at that point of time was so unusual that people didn't believe him. I mean, they said, "Oh, you must be joking," kind of thing. So we are going to hear a exposition on Galwa next week at the same time, I believe, at 9:30. So kindly join. I think you will get a link as usual, and then kindly join for the meeting. And the month after that, that is, it's almost 2 weeks. November 7th, we will have one more CC lecture, and that's going to be on another French gentleman, Albert Camus, and that's on philosophy. He started a new wave of philosophy in the 1960s, and even today, people are still thinking about and writing about what Camus said and what the implications are. So we are going to discuss about Albert Camus on the 7th of November. So I leave it at that, and then if Professor Murthy wants to say anything, then that's what.
That is just one, because the entire the concept of CAC was introduced by Professor Jamdagni. I think we are extremely happy that the lecture next week, the CSC lecture next week, is the 10th one in the series. I think we have been doing it in the last 1 year. It has received good appreciation and good amount of following. I think we'll continue to do that going forward. I take this opportunity to thank Professor Vittal Rao on behalf of Bytes for taking time off his busy schedule to be with us. And I'm so fortunate to get his time regularly for Bytes, particular lectures. I think Fourier, then Fourier Transform today. I think next week we have one more lecture by Professor Vittal Rao, and a few more lectures that are going to follow. We are extremely happy that the response has been overwhelming. There were as many as 295 participants on the Zoom link, and there were a good number of people outside Zoom link, also in the YouTube Live and others. There were good number of participants who were attending the lecture from Coimbatore and other parts of the country, which was a good sign in terms of the content, and we are able to reach out to more people in terms of this. And we also take this opportunity to thank the Dayanand Sagar University, particularly Professor Srinivas and Madam Mahalakshmi for facilitating the entire thing. And Bytes would like to thank Mr. Imtiaz for doing a wonderful job in terms of providing us the link and maintaining the entire thing. And I'm sure the lecture was very interesting, and the kind of narration that was given, the kind of summary that was given to us is phenomenal. I think the last 3 or 4 were fantastic in terms of the understanding of the power of Fourier transform. Sir, we are truly honored by your consent to deliver lectures for wide audience. It will continue to trouble you in the future also. We request you to consider our request and give your valuable time for us, so that the more students and faculty stand to benefit. There were a good number of students this time. There were close to about 150 to 160 students also attended, and all of them have written back to us saying that the lecture was very, very good. Thank you, sir. Thank you very much.
Thank you. Thank you.
One small thing particular to our student community, it's no coincidence that we had Fourier, and then we are going to follow it by Galois, and then we will have Albert Camus. Many of them are really French intellectuals. And if you take the 18th and 19th and 20th centuries, lots of intellectuals came from that particular region. I don't know what DNA they have in that place. So what I strongly recommend to our students is just look at a little bit of history of all these intellectuals of the past. Actually, Professor Vittelrau quoted also Marcel Proust. And Proust is one of the biggest names in those days. And then we have Blaise Pascal, and then so many. I mean, you can keep on Laplace and so many. And so how come that there was such an intellectual atmosphere and such an intellectual growth in a very small region of the world? I think it is good to contemplate, because we had this same in our country for a long time, and we want to bring back that. You have a region, maybe whole of India, maybe Bangalore, maybe I don't know what, a region where people really across the fields, whether it is philosophy or art or maths or anything, they sort of sit together and contemplate and really think about the implications of a lot of this kind of new things and old knowledge that we had and the new knowledge that we are generating. And then that, I suppose, that I believe strongly is a very strong cultural element that the student community will have to take it from. There was one Jean-Paul Sartre, who probably he will come up in one of the lectures. And when he died, he was a philosopher and not a particularly fluent one. I mean, it's very difficult to read Jean-Paul Sartre. But when he died, there were 4,000 people in his funeral. What made France, and this happened about 40 years back. So what is that in France which actually makes people somehow revere such intellectuals and follow them closely, and then actually carry forward? It is not a blind faith. They don't say Jean-Paul Sartre was right. They attack him. They think that his theories are questionable, and then they discuss in depth. And that is the kind of intellectual culture that we want to create. And CEC, we want to start. Yeah, I mean, we want to start the CEC as the basis for this, so that we hear about these great people, and then we think about what their mind has been, what have they been doing, and why this impact happened, and what is the usefulness of what they have said, and so on. So I think particularly students group, I would encourage everyone to do it, but particularly students, I think we should not miss out on that. Please listen to all the CEC lectures and think about them and see the implications and see how we can bring back such a culture to the whole country. Sorry if it looked like a sermon, but I really think that we are missing it out.
Thank you. Thank you very much.
Yeah.